Hello, everyone. Sorry I didn't upload a lecture this week because I was busy with a lot of things like exams, TA duty, talks and research and etc. But today, well, I'm going to compensate by uploading two lectures, maybe this one on black holes and another one on postulates of quantum mechanics. So look out for that. Today, I'm going to talk about extremal black holes, BPS states, and their connections to supersymmetry and supergravity. So let's go. The outline of this lecture is as follows. First, I'm going to summarize what we did in the last lecture. Then I will talk about geometries of extremal black holes. Afterwards, I will talk about multi-black hole solutions and the Majumdar-Papapetrou solution. Then I will describe their connections with supersymmetry and supergravity theories. And finally, I will talk about superconformal algebras and BPS states. So let's go. In the last lecture, we derived the geodesic equations using the Lagrangian and Hamiltonian formalism, and we utilized Mathematica to compute the geodesic equations. So what we did is we basically wrote a Mathematica script, and we used two different methods. One where I actually computed the partial derivatives and the total derivatives, and other just using the variational methods package and just using the Euler equations command. So we obtained the geodesic equations, and then we tried to solve it in some very particular cases, like in the equatorial plane where theta is pi/2, and then we obtained the ISCOs and the conditions for the stable orbits. So after obtaining the conditions, I showed you how to plot phase portraits in Mathematica, and the black dot represents the location of the ISCO, and for Schwarzschild black hole, it's at about 1.5 Schwarzschild radii. And if we slowly increase the charge to mass ratio, and by increasing the charge to mass ratio, we see that there are two stable points, indicating that there are two ISCOs. And this makes sense because charged black holes have two event horizons, so it makes sense that they have two ISCOs. By increasing the charge to mass ratio further, we see that the stable points get closer and closer together. And then one of them exhibits a limit cycle behavior. By further increasing the charge to mass ratio, we see that the limit cycle behavior still persists, and the dots get closer and closer together. Finally, when we arrive at the extremal black hole case, we see that there's only the two dots coincide, and they form one event horizon, which is at half a Schwarzschild radii. And this makes sense because extremal black holes only have one event horizon, and it's at the r equals m radii. So today I will talk about the physical properties of extremal black holes, and even though they are not astrophysical, they have a lot of interesting physical and mathematical properties. Before I do that, we also talked about Killing horizons and their connection to Lie algebras and Lie groups. And I showed that by computing the surface gravity, we find that the surface gravity for extremal black holes is 0 at the event horizon. And this corresponds to 0 temperature. And this is a reason as to why extremal black holes are not physical, because according to the third law of thermodynamics, you can never reach 0 temperature in a finite number of steps. So now I will talk about the geometry of extremal black holes. So recall that a Rice-Nordstrom solution is extremal if the mass is equivalent to the magnitude of the charge. Then we will find the metric reduces to the following form. And to better understand the causal structure and geometry of spacetime, what we can do is we can write the above metric in null coordinates. And by doing so, we find that the u equals constant and v equals constant solutions represent the white and black hole solutions respectively. And using analyticity and isometries, we can draw Penrose-Carter diagrams by writing this in Kruskal coordinates and subsequently Penrose coordinates. By doing so, we obtain the following Kruskal diagram. We can see that the extended regions out here are cut, and then the singularity seems to cut these regions. And what we obtain is a Penrose diagram that is truncated on these two sides. What is interesting about this is that the Cauchy horizons at H plus and H minus represents surfaces of constant T. This is the same as in that of the Weisel-Nordström case. However, more interestingly, the surfaces where T is constant are not Einstein-Rosen bridges. And one can see that, this by computing the proper length for constant T, theta, and phi, and we find that this proper length diverges. Thus, this represents a wormhole with an infinite throat. And to understand the topology near the event horizon, what we can do is we can let R equal to M times 1 plus lambda, where lambda is some small parameter. And what we can do is compute this to leading order. And by doing this, we obtain the following metric, where we have these two parts and this part, and we have some higher order terms in lambda. And this is called the Robinson-Bertotti metric. And this has topology ADS2 cross S2, where the first two terms, well, ADS2 means two-dimensional anti-de Sitter space, and S2 is the metric for a two-sphere. And we can see that these two terms correspond to ADS2, as this term is very similar to that of the, you can see right here, this term here. It's very similar, right? So this term corresponds to the S2 region, and this term corresponds to the ADS2 region. And we can see this on an embedding diagram. So these two regions represent S2, and this is the event horizon region, and this is the region inside the throat of the wormhole. And to see the ADS2 region, it's a little bit more complicated, but we can draw it as an embedding diagram on a cylinder. So basically, the cylinder represents the ADS2 region, and then by we can. I obtained this diagram from the book by the book Supergravity in Friedman and Proyan. And what happened is that the shaded regions here represents the shaded region here. So this is an embedding diagram for the ADS2 region for extremal Weisel-Nordström black holes. So now that we've talked about wormhole solutions for the, not wormhole, sorry. So given that the Weisel-Nordström, the extremal Weisel-Nordström black hole cannot yield wormhole solutions, what is interesting is that they can still yield a multi-black hole solutions, and this is called the Majumdar-Papapetrou solution. This is similar to the Schwarzschild metric, and we use the same trick where we make the Weisel-Nordström metric spatially conformably flat. So by doing so, to do so, we just write it in the following form, where this form is the flat metric for a spatial flat metric for in spherical coordinates. And by writing this as a function of rho, what we do is by comparing this metric to that of this one, what we find is we get these two equations. And what we can do is we can eliminate phi by dividing one by the other, and we obtain a differential equation. And this differential equation is solvable because they're separable. And what we can do is we can integrate both sides. And what we find is rho plus a constant is equal to r minus m. And since the constant is arbitrary, we can just set it to 0. And what we find is that we get phi is equal to 1 plus m over rho. And from this, we obtain the following metric. And recall from the lecture on multi-black hole solutions for the Schwarzschild metric, the Yamabe equation states that for a spatially conformally flat metric, the nonlinear Einstein equations can be written as a linear Laplace equation. And thus we can superpose the masses, and we obtain the following solution. And this is known as the Majumdar-Papapetrou solution. So what does this look like on a Penrose-Carter diagram? I obtained this. Basically, what happened was Majumdar and Papapetrou independently derived this equation. But what happened is it was interpreted by Hartle and Hawking later, and they interpreted this as a multi-black hole solution. So what happens is they drew in this paper, they drew a Penrose-Carter diagram, and it's basically the Penrose-Carter diagram up here, but they conjoin the two regions and obtain this. And what does this look like in a space-time diagram? So in a space-time diagram, it looks something like this. So it's quite beautiful, I think. It looks like there's many, many light cones connected to each other. This is quite a beautiful depiction of charged multi black hole solutions for charged black holes. So what is interesting about this is that it is the simplest known example of something called this is the simplest known example of a supersymmetric brane solutions, and it is the simplest example of a supergravity theory. So before we discuss constructions of supersymmetry, I first have to describe the behavior of spinors. So I will define a spinor more formally when I discuss Clifford algebras in my series on mathematical structures of quantum theory. But for now, let us think of a spinor as a Euclidean space that transforms under SU2 transformations where the periodicity is 4 pi. This concept may seem unfamiliar to you, but you've actually seen them in life before. When I was at a party in undergrad, one of maybe a math or physics friend asked me, challenged me to, do something. Basically, I can show you. Maybe I'll stop sharing for a moment. And they challenged me, so hold your arm out like this and try to flip my wrist such that it is in this orientation without twisting my wrist. So I can show you how to do it. Maybe you can pause the video and try yourself. But what you need to do is first raise your arm, rotate this way, raise your arm, rotate this way, and rotate this way. Now, you can count how many rotations that you have, but you will see that you have obtained something similar to that of a spinor. So now let me share my screen again. So in this analogy, we can see, if you didn't like me doing that demonstration, what you can see is that you can try this on a Bloch sphere with a flagpole. So this is the rotations. So the spinors represent the rotations on a Bloch sphere. So you can see that the flagpole is in this orientation. To rotate it the other way, you need to do exactly what I did, raise it, rotate this way, raise it again, rotate this way, and you'll see the flagpole is in the opposite orientation. So, but mathematically, why is this the case? So let me show you that this kind of rotation in the context of SU2 groups. So recall that a representation of SU2 is as follows. And now consider the following transformation that is also in SU2. So basically it's this one, and we multiply the matrix out, we obtain this. So we can rewrite this as the following, and we can write this as z prime x, represent this as this new transformed coordinates as z prime, x prime, and y prime. And using Euler's formula, we can compare one of these terms with this term, and what we see is this, right? So we can see that x prime is equal to this, y prime is equal to this, and z prime is equal to this. This is very similar to that of a rotation transformation. So basically, if I wanted to rotate about the x-axis, I would need to multiply by cosine theta and sine theta. And what happens is, you notice that there's a factor of 2 here. This is interesting because this is the rotation in spinor space. You want to convert to Euclidean space, you had to divide by 2, and that means you would have cosine, not theta, but this is 2 theta, right? Let's say u equals 2 theta. So you would have theta equals u over 2. So the rotation in spinor space is twice that of the rotation in Euclidean space. So if you rotate by 2 pi in Euclidean space, you need to rotate by 4 pi in the spinor space. So this is another great geometric depiction of spinors. Basically, if you rotate about a Möbius strip, you obtain the opposite direction. Another way you can think of it is you can construct your own Möbius strip, rotate it 360 degrees, and you'll realize that you're on the other side. And to get to the same side, you need to rotate it again, not rotate, but go along the Möbius strip again to come back to the same point. So this is another way of thinking of spinors. So now that we've talked about spinors, we are ready to construct global supersymmetries. Now recall that the Dirac equation is as follows. I think this is not an m squared. I think this is an m. This is a mistake. This should be m, not m squared. So now where gamma is the Dirac matrix and psi is some spinor. Now, let us consider the case where m equals 0. Then we obtain the following equation. So this means the spinor is covariantly constant. And this is how we generally construct global supersymmetries. However, in general relativity, since we have curved spacetime, we cannot just simply use the partial derivative. We need to promote to the covariant derivative. And doing so, we obtain the following. However, the caveat is that we cannot construct global supersymmetries in general relativity. This is because if the covariant derivative of psi is equal to 0, if we take another covariant derivative, this is still 0, which further implies that if we take the commutator of the derivative, this is still 0. But recall that the Ricci identity states the commutator of the covariant derivative is related to the Riemann tensor. And the Riemann tensor tells us the curvature of space-time. So this, but notice that psi equal to 0 is a trivial solution, so it's meaningless, so we don't consider that. The Dirac matrices are representation dependent, but are generally non-zero. Hence, this implies that the Riemann tensor must be 0, which means that for a 0 Riemann tensor, this is a flat Minkowski space. So for us to construct global supersymmetries, we can only do it in Minkowski space-time. Hence, it is impossible to construct global supersymmetries in curved spacetimes. Fortunately, however, there's a loophole, and instead of constructing global supersymmetries, one can construct local ones. That is, the spinors must depend on time and space. And this is the key to supergravity. I will discuss supergravity in more detail when I discuss positive energy and mass theorems. But to contextualize this lecture, I will mainly focus on one particular theory of supergravity, which is n equals 2 supergravity. And for reference, if you want to read more about supergravity and learn more details, I would recommend the book Supergravity by Friedman and Proyen. This is very, very good. I read it for maybe 2-3 weeks, and I not completely understand, but I understand enough to talk about supersymmetry in the context of black holes. And I will save the discussion of n equals 2 gauge theory in my quantum mechanics and particle physics lectures. So let me talk about the idea of supergravity. So basically, before I stated that we need to construct local supersymmetries. What this is doing is we are constructing a set of local coordinates where space-time is flat. So the idea behind supergravity is similar to that of the differential forms, where we construct a spin connection where the space-time is locally flat. So you can see here we have a curved space-time. And what happens is we construct a set of local coordinates, namely these ones, such that the space-time is flat in this region. So this is the idea behind supergravity. So in this lecture, I will mainly focus on 3+1 dimensional space-time. And for 3+1 dimensional space-time, superconformal algebras for the n equals 2 group. The superconformal algebra for n equals 2 is the group SO4, 2. And the generators of the algebra is as follows. I separate this into 2 because superconformal algebras are different to that of conformal algebras. So conformal algebras represents conformal transformations, but they only have one type of Lie bracket or super Lie bracket in this case. So the first one are called the bosonic generators, which have Lie brackets as the commutators, whereas the latter one are these superconformal algebras associated with fermionic generators, and the Lie brackets are that of the anti-commutators. So superalgebras actually have 2 types of Lie brackets. So this is why we call them superalgebras. So P, K, M, and D are the generators associated with linear momentum, boost, rotation, and dilation. Whereas the Q and S supercharges are something called conserved supercharges. And here the Latin indices denote a particular supercharge. So the generators have the following commutation relation, and I don't expect you to remember this, as you can search them up anywhere, but I just list them out here for reference. And the main question is, how does this relate to extremal black holes? Well, before we can see the connections. We need to define something called a killing spinor and BPS states. So a killing spinor is a spinor where the Lie derivative vanishes. Spinor Lie derivative vanishes. So this is the spinor Lie derivative, and basically it's similar to the Lie derivative of that of vectors and tensors, but we have this additional term with gamma matrices and this commutator. And BPS states are basically massive representations of an extended supersymmetry algebra. And they have a mass equal to that of a supersymmetry central charge Z. So what is the connection between the two? Well, in both this killing spinor and BPS formalisms, the component of the bosonic fields are related by a first-order differential equation. And as a result, in supergravity theories, BPS states and killing spinors are equivalent. Now, let us show that the Majumdar-Papapetrou solution is a BPS state. So consider, well, I wrote, this need not be the Majumdar-Papapetrou solution. So any metric that satisfies has the following form can be shown to be a BPS state. So for the Majumdar-Papapetrou solution, e to the minus f is equivalent to this. Now, recall that the covariant spinor of derivatives is as follows, where omega alpha ij is the connection 2 form, and omega ij is the spin connection. So from the lecture on Birkhoff's theorem, the orthonormal bases for the Majumdar-Papapetrou solution are as follows, and the spin connection 1 form are as follows. And if you don't remember how to compute these, go back to the lecture on Birkhoff's theorem, as this is exactly the same as the differential forms formalism. So now let us examine the killing spinor along the time-like killing vector field, and suppose that the killing spinor epsilon satisfies the following, satisfies the spinor Lie derivative equation, where the spinor Lie derivative vanishes, and we obtain the following equation. And since the metric is static, it is reasonable to infer that the killing spinor is time independent, and hence the first term in the above equation vanishes. So this one vanishes because this is independent of time, and the partial derivative with respect to something that is independent of time is 0. We can see that the killing spinor condition can be satisfied if the following equation is satisfied. So by Killing's equation, this basically this term reduces to 0 because, well, we showed that partial t of epsilon I is equal to 0, and by taking the partial derivative, so we are left with this term. But Killing's equation is satisfied when this is equal to 0. So this is 0, and hence this is 0. So by taking another derivative, what we find is we obtain we take another partial derivative with respect to I, we obtain the following equation. And what we do is we can see that the first term in this equation vanishes because once again, we have this term here, partial I, psi t is equal to 0. So then hence this whole term is 0. And this implies that this function here is equal to 0. And this is similar to the Laplacian, remember? So this is exactly the same as what we showed up here. It's exactly the same as this equation up here. So we can see by, well, so this equation is satisfied. Thus, e to the minus f is a harmonic. So by obtaining this, we show that this is also a harmonic function. And this is not generally the case, though. I must mention, just because e to the f is a harmonic function does not mean e to the minus f is a harmonic function. It is just this case that is particularly special. And we have shown that since e to the minus f is harmonic, it means that you can superpose masses over each other. And this is exactly why we call them supercharges in supergravity, because similar to electromagnetism, in electromagnetism, if the Laplace equation is satisfied, you can superpose charges. In this case, you can superpose masses, and thus those masses are analogous to charges. And we can see that the Majumdar-Papapetrou solution satisfies this condition because e to the minus f is simply this, which means that the Majumdar-Papapetrou solution is a BPS state. And this is quite beautiful, as we can see that extremal black holes are a result of n equals 2 supergravity. And moreover, we can see the connection between supergravity and general relativity, as they both imply that e to the minus f or phi must be a harmonic function for a supersymmetry to be preserved. So the next damning question we have is, what does this have to do with superconformal algebras? Well, to see this, we need to compute the killing spinors along the space-like killing vectors. Basically, in the previous case, we only computed them along the time-like killing vectors. If we do this for the space-like killing vectors, we find that the Lie spinor derivative vanishes if this equation is satisfied. And hence, it has a solution, epsilon equals some constant times e to the f over 2. And these spinors are really cool because they have 4 real components which correspond to p alpha, m alpha beta, q, and s. K is not included because we are taking the spatial derivative, and K is associated with boosts, which has times translations. This means that the Majumdar-Papapetrou solution preserves 4 out of 8 supercharges in the n equals 2 superalgebra. And this is why they are called the half BPS states. And moreover, this is really interesting because the P alpha is associated with 4 momenta, but 4 momenta has basically the 0 component is energy, and energy is essentially mass in general relativity. And what happens is, by doing this, we see that since P alpha satisfies a superconformal algebra, the mass can be superposed because they satisfy a commutator relation, which is really, really cool. So surprisingly, superconformal charges and superconformal algebras have a nice connections to Hamiltonian flow. I will talk about this later when I actually do a lecture on supergravity, but this has a connection to something called black hole attractor mechanisms. So what is this? Extremal black hole solutions of n equals 2 supergravity have a scalar charge that exhibit a gradient flow towards the fixed points at the killing or event horizons. The positions of these fixed points are only dependent on the charge carried by the black hole. The Hamiltonian flow is dictated by the black hole's potential related to the central charge of the n equals 2 superalgebra. And I will discuss this further when I discuss a more generalized theory of supergravity. For now, let us see the motivation for this. So remember, before we talked about the ISCOs for Rice-Nordstrom black holes, and we computed the position of the fixed points, and then we plot them on a phase portrait, and we can see that this has a Hamiltonian flow towards the event horizon, and this is similar to that of the black hole attractor mechanism. However, we did not try to change the charge, and we didn't see much difference in the fixed point, and this is because in the black hole attractor mechanism, they not only do they have electric charge, but they also have magnetic charge, which seems to imply for the existence of magnetic monopoles. So this is quite an interesting connection between supergravity theories and general relativity. So I hope you've learned something, and I hope you find this connection between the two theories beautiful, and I'll see you in the next lecture. Thank you.